It's been a fantastic night. And as I've said in my speech, we really need to celebrate our technologists as much as we celebrate our sports people.
And we've got to keep encouraging people to get into the STEM.
Yeah, absolutely. I think quantum computing in particular is a very niche and new area. So creating that awareness and understanding about the opportunity around this space is incredibly important. So being able to have that reach and creating that new audience, I think is super important. So these events, I think, are critical to the success of quantum computing in Australia.
When people say, what does an electron look like? Everyone just imagines it's just a probability density, it's just a Gaussian decay. But then when you look at it in the crystal, it interacts with all the bonds, all the electrons in the bonding. So it's actually incredibly rich. And so there's a high probability the electron will stay near its nucleus. So there's a bright spot there. But then it interacts with the diffraction of all the atoms. And so this is unbelievably. And so you're making a qubit where you're encoding on that state. And we know, because we can see it, that state is complicated. Whereas other people just imagine it's a cloud. And once you've seen it, you can't unsee it. So you know what it is, but they haven't really ever seen it in that system.
So absolutely inspiring evening, and I am very much excited to see where this all goes.
Welcome to you all this evening. We gather to celebrate the achievements of our nation, our entrepreneurs in technology, and our future at the forefront of the state-of-the-art information and communications technologies. It's particularly pleasing to be welcoming you in this, our Jubilee year, as Kelly mentioned. And I'd like to acknowledge that Pearcey Foundation was started by a guy called Ian Dennis, who's unfortunately not here, but who's still prominent in the industry, particularly with the Australian Computer Society. I'd like to extend a warm welcome to Professor Michelle Simmons AO, our orator for this evening, and whom Jordan will introduce in more detail a little later. Another warm welcome also to the Honourable Ben Carroll, MP, the member for Niddrie, and the Minister for Industry and Innovation, Manufacturing Sovereignty, Employment, Public Transport. Quite a complex portfolio. We are very pleased to have you with us tonight, Minister, and thank you for your support. Otherwise, we wouldn't have been able to put this on. I'd like to also extend my thanks to other guests from the Victorian Government who are with us this evening. Amanda Caples. Is she here? Amanda? Yes. Hi, Amanda. She's the lead scientist at the Victorian Government. Danny Jarrett, Deputy Secretary, Industry, Trade and Investment. Connie Chrysafi, the Executive Director, Innovation and Technology, and other members of the department who are joining us here this evening. Particularly thanks must go to the members of the Digital Innovation Futures team who run the Digital Innovation Festival, the DIF, which is on this last couple of weeks. And we're extremely proud to have partnered with DIF since its inception, some 8 years back. And we very much look forward to many more years of engaging with DIF. Tonight, we're privileged to be both the grand finale of the Digital Innovation Festival and the midweek highlight of the Melbourne Connect Innovation Week. We've already had an event this week on the Melbourne Connect Innovation Week. Dr. Thorne spoke about some of the history of computing at Melbourne University. And I want to especially thank the Vice-Chancellor of the University of Melbourne, Professor Duncan Maskell, who's here tonight. Really appreciate you coming along. I'd also like to welcome Professor Frank Viteri, Deputy Dean Engagement, the Faculty of Engineering and Information Technology, and other University of Melbourne friends joining us tonight from the Faculty of Engineering and Information Technology, the Faculty of Science, and the Faculty of Business and Economics. We also have a table of friends from the Silicon Quantum Computing team based at the University of New South Wales. Thank you very much for making the trip down to the deep south to be with us tonight so you can share with us all in hearing Michelle deliver the oration. It's my particular pleasure to welcome and thank our friends and colleagues from the Australian Computer Society who are joining us tonight, and in particular 3 members of the Management Committee, that's the national board that governs the society. First of all, Mr. Rod Dillner, the chair of the ACS Victoria branch, the Victorian Congressional Rep, and someone I've worked closely with for many years. Ms Helen McHugh, the ACS New South Wales Branch Executive Chair and the New South Wales Congressional Rep, and Ms Jo Dalveen, Vice President, Membership Boards. We're excited to have the ACS joining us, a partner in Australia 4.0, a major initiative I will describe a little more about in a minute. The Foundation has a special partnership with ScienceWorks Museum, the current home of CIRAC. Together we work to inspire the youth of today to be the ICT pioneers of tomorrow. Earlier today, our orator, Professor Simmons, joined with us at ScienceWorks for some hands-on inspiration with the children who happen to be there this afternoon. We're very pleased also, as Kelly mentioned, to have Jonathan Shearer, General Manager of ScienceWorks, who's been able to join us once again for the oration. Just let me reflect a moment on how we happened to hold the Pearcey Oration. The first oration was held in Sydney on the 11th of September 2008 and was delivered by Dr. Terry Cutler, the late Terry Cutler, some of whom I'm sure you will recall. He happened to be Deputy Chair of CSIRO at that time. He had been invited to review Australia's national innovation system by the then Federal Minister for Industry, the Honourable Kim Carr. It was a seminal document, and we were very proud to facilitate the first publicly release of the review in a presentation he entitled Not Waving but Drowning. Perhaps it was a reflection of his mindset at the time. As I recall it, Terry was very nervous that evening, given this report was a hot potato politically. Senator Stephen Conroy, then Minister for Communications, was also in attendance to present the Pearcey Medal. This was right in the middle of the announcement of the NBN, a long time ago. As well, in the audience that evening was the Honourable Fran Bailey, former Howard Government Minister, who also happens to be here with us this evening, and whom I might add, Senator Conroy graciously acknowledged her presence even though she was in opposition. That evening, Terry also presented the 2008 New South Wales Pearcey Entrepreneur Award to Mike Cannon-Brooks and Scott Farquhar of Atlassian. And by the way, Michelle, he also presented the Pearcey Hall of Fame that evening to Dr. Neil Westy, who's famous in the semiconductor industry for VLSI and on CMOS. If you get all that, there's a test at the end. Whilst Terry's speech was notable, and we have it on our website, let me read a few lines he made in his remarks, and which I am sure you will agree reflect wonderfully well on our 2023 orator. Trevor Pearcey and the awards made in his name remind us that innovation and advances in technology and industry are fueled by talented and creative individuals. Creativity in science, industry, or the arts is the ability to envision alternative futures and new possibilities for our society. And I would suggest we're here tonight to celebrate that we are capable of all those great things. We have held the oration annually ever since, excepting during COVID, and that since that day in September 2008. We've had some notable orators over the years, all of whose speeches are recorded and on our website. Last year's orator was the current Minister for Industry and Science, the Honourable Ed Husick, delivered here right in this room. I'm proud of this initiative, which sets out to encourage leaders in our industry to comment on major issues of the day. Hence, Michelle is speaking about quantum computing. While the oration is our perennial effort, each year we adopt one other major initiative in thought leadership and national collaboration. This year it is Australia 4.0, a series of national discussions culminating in a half-day summit in Sydney at the end of October. A net zero emissions electricity distribution network model based on renewable energy sources changes many of the assumptions underpinning our existing electricity infrastructure here in Australia. The intersection of advanced ICT and this grid transformation process is not only incredibly challenging, but also very difficult to comprehend in its magnitude. To date, we have run 5 national sessions regarding some elements of these challenges, the latest of which was Monday of this week, involving some 220 online participants. We are viewing these challenges through a digital and data lens, smack in the middle of what ICT is all about. There are 2 remaining online sessions to be followed by a summit on the 30th of October in Sydney, where we will present our findings and propose a follow-up program for 2024. We have many partners in this initiative, in particular the ACS, who are sponsoring us to hold these events, and the University of Melbourne, and the Monash University and the University of New South Wales. Full details on this ambitious program are all on our website. I hope you are all as excited as I am about the opportunity we have as a nation in front of us. With the full knowledge, we have great capabilities to address these challenges. And now I'd like to welcome to the dais Jordan Green. Jordan, amongst other prominent roles in the formation and leadership of Australian innovation ecosystem, is chairman of the Victorian Pearcey Committee and secretary of the Pearcey Foundation Board. Jordan.
It's certainly our privilege and good fortune to have her with us tonight, Professor Michelle Simmons AO, to deliver the Pearcey Oration. Michelle is an internationally renowned Australian scientist recognised for creating the field of atomic electronics. Australian of the Year in 2018, a recipient of the Order of Australia, Professor Simmons is one of the few researchers in the world to be made a Fellow of the Royal Society of London. In 2021, the Royal Society awarded Michelle the Bakerian Medal and Lecture, the premier recognition in physical sciences. The honour was in recognition of her seminal contributions to our understanding of nature at the atomic scale by creating a sequence of world-first quantum electronic devices in which individual atoms control device behaviour. So I'm an electronics engineer. When I read about one transistor being made out of 3 atoms, I was really excited. Michelle is the director of the Australian Research Council Centre of Excellence for Quantum Computation and Communication Technology at UNSW. She has been recognised by the American Computer Museum as a pioneer in quantum computing. Also in the USA, Michelle was awarded the Foresight Institute Feynman Prize in Nanotechnology and was named the 2017 L'Oréal UNESCO Asia-Pacific Laureate in the Physical Sciences. She was the inaugural editor-in-chief of Nature Quantum Information and has been chair of the American Physical Society Division of Quantum Information. After completing her PhD at the University of Durham in the UK, Dr. Simmons went on to do postdoctoral research at the Cavendish Laboratory at the University of Cambridge. I was able to discuss that with Vice Chancellor Duncan Maskell this evening, who also was a Senior Pro-Vice Chancellor at Cambridge. For the last 22 years, she's been at the University of New South Wales in Sydney. The university has given Michelle the opportunity to take risks and build a sizable team in this pioneering field. Professor Simmons is proud and appreciative of the university and of her team, and I believe the feeling is deeply reciprocated, as we see from her team members who are with her tonight. Her team is at the forefront of a global race to develop a quantum computer in silicon. Michelle isn't waiting for the research to be complete, though. She has already launched her company, Silicon Quantum Computing, and in doing so, she has laid the foundation to drive the opportunity for Australia to master this new manufacturing challenge and become a powerhouse for the supply of quantum computing components in the 21st century. I recognise a friend of the Pearcey Foundation with us tonight, Mr. Peter Yates, who is also a board member of Michelle's company. We're a connected community at the forefront of pioneering technology. Michelle says few things have given her greater pleasure than hearing she was awarded the Bakerian Medal and that she would give the Bakerian Lecture. We hope that in some way she can be as inspired and recognised here tonight in the community of her adopted home with the Pearcey Foundation and all of you celebrating her and her vital role in lifting our nation into the fundamental science and industry of this century. Ladies and gentlemen, Professor Michelle Simmons.
Good evening, ladies and gentlemen. Well, so Trevor Pearcey was a true technological pioneer and a great Australian. CIRAC, the computer he and his team built at CSIRO in the 1940s, was a triumph of groundbreaking electronics and ingenuity. And for these reasons alone, it's an honour to deliver the oration in his name. But I can also take extra delight in this moment because Trevor and I had a few more things in common. We both started life in the UK and migrated to Australia early in our research careers. We both had ambitions to build a new kind of computer, in each case one that was at the very forefront of what was humanly technologically possible. I believe we also both shared the view that we should not underrate Australia's potential as a place for commercialising and industrialising computing technologies. And these are all themes that I'm going to touch on today. One of the things that I find fascinating about the CIRAC, and I saw it today at Melbourne Science Work Museum, is its size. The computer was the state of the art in its day, built using 2,000 vacuum tubes, that period's vision of our modern day transistor, each big enough to hold in your hand and stacked together in banks. The machine filled an entire room. And I know I'm not the first to point out that the contrast with our modern calculating machines, but it's astonishing to think that in comparison with the current Apple M1 Max chip, manufactured by TSMC, it manages to fit 57 billion transistors into one thin sliver of an object about the size of an after-dinner mint. But computers are not the only technology that's shrunk over time. The first motors were enormous, big, bulky, steam-powered engines, originally designed to pump water out of mines. But now you can find miniature electronic motors all over the place in refrigerators, dishwashers, vacuum cleaners, cameras, and of course in the ever-expanding transportation technologies. The first mechanical clocks were also rather grand and expensive, so much so that the earliest mechanical chronometers were largely to be found in significant places like churches, cathedrals, and town halls. Whereas today, anyone can buy a watch, and our whole world has become synchronized as a result. Or think about printers. Gutenberg's printing press was twice as high as a man, larger than a grand piano, and arduous to use. Yet now you can pick up an efficient laser printer that's almost the size of the palm of your hand. The miniaturization of computing, therefore, is not an entirely unique story. One of the ways that humans can enhance any technology is to try and miniaturize it. And it's not uncommon that, having made something smaller, we find unique ways of using it, which end up transforming society in unanticipated ways. The story of computing is, however, unique in scale, if not in kind. And I say this not just because of the stark comparison that might be drawn between the CIRAC of the late 1940s and the wild multitude of conveniently sized and extremely powerful computing devices we all have at our disposal today. What truly sets computing apart from other technologies that have miniaturized is the sheer speed and the scale of the miniaturization, and the unbelievable fact, as I will explain this evening, that we've now brought this particular process to the ultimate limit, whereby the core features of our computing machinery can actually be reduced to the size of individual atoms. I'm sure everyone here has heard of Gordon Moore. Gordon Moore was the co-founder of Intel. He's the one who first noted that the number of transistors on a microchip was doubling roughly every 18 months to 2 years, which essentially means in practical terms that the smallest feature size on these chips was halving in size over the same time frame. Moore published his data in the 1960s and projected the rate of growth into the future, observing that if any semiconductor company wanted to remain competitive over time, it would have to keep cramming more and more transistors into even less and less space. And in doing so, he set a standard that the entire industry benchmarked itself against. And he turned what was essentially an observation of only a few years of data into a self-fulfilling prophecy that actually lasted for decades. 30 years later, in the late 1990s, when I was working at the Cavendish in Cambridge and considering migrating to Australia, people were still looking at the same data on the number of transistors on a microchip and wondering about the forward projection. Because back then, judging by the speed at which the semiconductor industry was moving, it looked as though it would be about 20 years or more in the early 2020s that companies would find themselves making devices with feature sizes at the level of individual atoms. But in those days, of course, there wasn't any technology that would make such a thing possible. But there were microscopes that had been invented in the late 1980s, or the 1980s, the scanning tunneling microscope, that enabled us to actually visualize atoms. So I decided that I would come to Australia and I would see if I could adapt this technology of this imaging tool to leapfrog the projections of Moore's law and build electronics at the atomic scale on an even faster time than what was predicted. It was not a totally stupid idea. In fact, there had been a precedence for it. The scanning tunneling microscope that allowed us to see for the very first time that atoms exist has a very fine metal tip that you bring down to the surface under voltage control. And when you bring this tip close enough under a vacuum, a tiny current starts to flow between the tip and the atoms on the surface. And to image the surface, you keep that current constant and you drag the tip across the atoms, thereby building out the heights of the atoms on the surface. You raster scan that across the surface and you can build up a topographic image of what all the atoms look like. And that was really the first time that people knew that atoms existed. But in the 1990s, researchers at IBM turned this idea on its head. Instead of just looking at the atoms on a surface, they wondered whether you could use that same tip to actually pick up atoms and move them around. And they famously formed the world's smallest logo, IBM, by applying a voltage to this tip to pick up atoms on a metal surface, moving them around and pulsing the tip again to drop them off in a new location. And our hope was that we could use that same kind of technology to try and put atoms in place in a semiconductor crystal. The problem was, it wasn't easy. The bonds in a semiconductor crystal are just far too strong. So we had to come up with another way, a much more complicated way, to make atomic scale devices in silicon. Our atomic fabrication method, which is really a product of 20 years of research by my team, did end up using that scanning tunneling microscope. But it also mimics the lithographic process that you would find in a conventional clean room, like an Intel clean room. And it works as follows. We start by taking a wafer of silicon and we etch markers into the surface so that once we've made our atomic scale device, we can come back and find it again because it's so small you can't see it with the human eye. And we call these markers registration markers. Next, we load our wafer of silicon into an ultra-high vacuum system, so it looks a bit like a spaceship, of the scanning tunneling microscope. And we heat it up to 1,000 degrees, which melts the surface, and then we cool it down really slowly so we can reconstruct it again. And this forms these beautiful rows of clean silicon atoms at the surface that we image. We then introduce hydrogen to the system, which basically covers the whole surface with hydrogen. And now's the fun part. Using that very fine metal tip of the scanning tunneling microscope, we now desorb selected hydrogen atoms from the surface in the same way that IBM did with the metal atoms by moving them around. And we literally write into the surface to expose the underlying silicon. This gives us a mask that is mainly hydrogen with gaps and holes in it. We now want to bring in the atoms that make up the active components of our device. In this case, we're using phosphorus atoms, which is an element in the periodic table that has one extra electron compared to silicon. We supply these phosphorus atoms using phosphine gas, which sticks to the exposed silicon, but not to the surrounding hydrogen. Some magical chemistry occurs at this point. The formula for phosphine gas is pH3. So when you heat the sample up, the phosphine starts to shed its hydrogen atoms. One by one they go. And eventually the phosphorus atom, deprived of all its hydrogens, will drop itself into the top layer of the silicon and push a silicon atom out. We then take this device across to another system, a crystal growth system under ultra-high vacuum. It's a technology called molecular beam epitaxy. And we encapsulate the whole thing with silicon at low temperatures, atomic layer by atomic layer, to make sure that our phosphorus atoms don't move and will remain stable. If we want, as a check, we can use that scanning tunneling microscope to image the atoms beneath the surface to show they're still there, exactly where we put them. And finally, we can take the device out of the ultra-high vacuum system and move it through to a clean room where we use those all-important registration markers etched into the silicon at the start to make contacts to the buried device below. It took us a long time to figure out this process. It required some of the most sustained and systematic problem solving of my career. And despite having outstanding students and postdocs working with me on this, it took nearly 10 years to perfect it. And of course, it's something we're still refining now, even though our yields are incredibly high. But it was well worth the effort because our approach to atomic fabrication culminated in the world's first electronic devices engineered from the ground up in which the core components are designed and made of using just a few or even single atoms. Among the atomic scale devices we've made is the 7-atom transistor, which was picked up by the Guinness Book of Records, as my son discovered one day, to his surprise when he went to the school library. In fact, it was more than just a simple transistor. It was quite an interesting device because it gave us 7 different charge states as we removed electrons from those phosphorus atoms. We've also made tiny, tiny wires out of phosphorus dopants. In fact, we've shown that we can pattern these wires so thin they're just 1.7 nanometers or 17 angstroms, a few atoms wide, 4 atoms wide, and it conducts electricity as if it was made of copper, proving that Ohm's law is maintained all the way down to the atomic scale. Now, this is very, very important for us because it allowed us to build much more complex devices where we can bring these wires down and we can move charge around in the device on the atoms that we've put in the system. And because these wires are made of phosphorus in silicon, they have very high frequency transmission of electricity and very low noise. And then, of course, there's the single atom transistor, where we designed and built a device with a single phosphorus atom situated between gates, also engineered from phosphorus donors in silicon, so that we could load individual electrons on and off a single atom to switch it from on and off conducting states. That device was exciting not just because it was a technological landmark. It also enabled us for the first time to see what the electron wave function looks like. What does an electron wave really look like in a silicon crystal? And somehow, quite miraculously, we could use the same scanning tunneling microscope to see how the wave function of the extra electron on that atom looks like. Now, we managed this all within a decade, ahead of the timeline projected by Moore's law. But let me tell you something that's even more astonishing than that. There was someone else, even before Gordon Moore's famous paper, who saw all this coming. Back in 1959, just 10 years after Trevor Pearcey's CIRAC was completed, at a time when commercial computers were just being built with transistors, when they only started being sold, and more than 25 years before the invention of this microscope that allowed you to see atoms, the Nobel Prize-winning physicist Richard Feynman, one of the world's great visionaries, gave a lecture entitled "There's Plenty of Room at the Bottom." The subtitle of his lecture, which I find even more interesting, was "An Invitation to Enter a New Field of Physics." So right at the outset, he stated that what he wanted to talk about was the problem of manipulating and controlling things on a small scale. And he asked why we shouldn't aspire to make circuits and machines at the level of perhaps 10 or 100 atoms. "I'm not afraid," he wrote, "to consider the final question as to whether ultimately, in the great future, we could arrange the atoms the way we want, the very atoms all the way down." What Feynman grasped was that achieving such a goal was a problem of practicalities, not principles. He said, "The principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. It is not an attempt to violate any laws of physics. It is something in principle that can be done. But in practice, it has not been done because we are too big." Well, not anymore. I first read this wonderful lecture years ago and forgot about it, and it was only recently that I rediscovered it and realized just how well we've been delivering on Feynman's vision. Sometimes what seems like science fiction actually does come true, even if you have to wait 60 years. And there's one part of Feynman's vision, however, that we're still delivering on. Feynman was a quantum physicist. He won his Nobel Prize for quantum electrodynamics. He was not an experimentalist, but he deeply understood the implications of controlling things on an atomic scale. That is why, at one point in his talk, he says, "When we get to the very, very small world, say of 7 atoms, they behave nothing like they do on a large scale, for they satisfy the laws of quantum mechanics. So as we go down and fiddle around with the atoms down there, we're working with different laws, and we can expect them to do different things. We can manufacture in different ways. We can use not just circuits, but some system involving the quantized energy levels or the interactions of quantized spins." In this, once again, Feynman was right, for using quantized energy levels and the interactions of quantized spins is our next frontier, and the 20th century's next frontier in computing. Having figured out over the last 20 years or so how to make atomic electronics reproducibly and with exquisite precision, we're now starting to bring all the various components together to control quantum effects and see if we can exploit the quantized spins of electrons of phosphorus donors in silicon to make a quantum computer. And for those of you who may not have heard the exciting news, a quantum computer is a new type of computer that exploits the laws of quantum physics, so that instead of performing calculations sequentially like a conventional digital computer, it works in parallel, looking at many possible outcomes at the same time, and producing an exponential speed up in computational power. The concept is as novel relative to the digital computing machines that surround us today as Trevor Pearcey's computer was to the mechanical calculating machines of the late 19th and early 20th centuries. It is based upon the idea that if you can control quantum effects, such as the spin of an electron, then you can encode information in a quantum level in much the same way that a classical computer encodes information on its transistors. We should note, however, that information on a transistor is termed a bit. Information in a quantum computer is called a quantum bit or a qubit. These different terminologies are used because there are fundamental differences between the two paradigms, as I'll try and explain. Consider for one moment an electron. An electron is a quantum particle and a wave, and one of the quantum properties of an electron is its spin. To a physicist, spin has no analogue in the macroscopic world. However, we're often talking about an electron being either spin up or spin down. And in this respect, we can think of a spin as corresponding to a magnetic field, something like a tiny bar magnet. Indeed, it's this property that enables us to use spins to encode information. For example, it can align with a magnetic field, giving the 0 of classical information, or it can flip to align against the magnetic field in a higher energy state, giving the 1 of classical information. But there's more to the quantum world than ones and zeros. The quantum world is far more sophisticated than that, because of a property called superposition. It turns out that the electron spin can be in some fraction of its up state and some fraction of its down state at the same time. A quantum bit or qubit, in other words, encoded on an electron spin, does not just hold information as a 1 or a 0, as in the case of a classical bit, but it encodes information in a mathematical vector, with a fraction specifying 0 and a fraction specifying 1, providing 2 additional bits of information. Now, consider what happens when we bring 2 electrons together so they become entangled, another quantum property. On its own, each electron will have its own individual spin state, but when they become entangled, they create a new combined state based around the 4 possible spin pairings: up, up, down, 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 up, and up, down, or 1, 1, 0, 0, 0, 1, or 0, 0. Hopefully I got that right. Once again, though, because of superposition, the entangled pair can encode information as some fraction of each of these 4 states at the same time. Mathematically, this means that the spin of 2 entangled electrons will now hold 4 additional bits of information. And this pattern is repeated every time we add another electron. Now, imagine that these spins are used to store information as quantum bits or qubits in a quantum computer. In computing terms, every time we add another qubit to the system, we essentially double the amount of information the quantum processor is able to compute. So with 2 qubits, there are 4 states. With 3 qubits, there are 8 states. With 4 qubits, there are 16 states, and so on. So by the time we get to 30 qubits, our system now contains more information than a classical computer with 57 billion transistors. So this is not the only marvelous thing about a quantum computer. It should also be said that any computation operation we perform on an entangled state like this will be performed on every of the individual entangled elements at the same time. So this is totally different to classical computing. We must laboriously work through all the calculations sequentially, one after the other. So it really enables us to do parallel computation to an unparalleled degree. So Richard Feynman was absolutely right. You can indeed use the interactions of quantized spins to do things differently. The quantum phenomena of superposition and entanglement create potential for a completely new and uniquely powerful mode of computing. And if you can reliably initialize, control, and measure the spins of individual electrons and individual atoms, you have a superb platform for being able to do this. And this is where our atomic electronics comes into its own. Our now proven ability to engineer the placement of phosphorus donor atoms into a silicon matrix with sub-nanometer precision creates a perfect platform for exploiting the power of quantum physics in information processing. Phosphorus has one extra electron and one proton compared to its silicon host. It is consequently on the spin of the phosphorus electron, or the spin of the phosphorus nuclei, that we can encode our quantum information to create our quantum bits. And at the same time, silicon is an ideal host material for our qubit because it naturally forms a nice protective crystalline environment to host the qubit and keep it in place. Significantly too, the technology that we've developed not only makes the qubit out of the phosphorus atoms, but all the electronic components in the processor too. From the control electrodes, those wires that we put currents down and control the spin states, to the sensors, to the amplifiers, the capacitors and the inductors. Everything we make is on one monolithic chip, and it's made of just two atoms, phosphorus and silicon. This brings huge advantages because it means we don't have any materials interfaces or imperfections that are known to cause defect states and cause what we call decoherence, cause the quantum computer to lose its information. So working with just two kinds of atoms is simple, elegant, clean, and it enables us to form stable, high-quality qubits. Indeed, let me share with you two quantifiable examples of just how advantageous atomic systems are based on phosphorus and silicon for creating these high-quality qubits. First of all, with our atomic scale devices, we can read out the spin state of a single electron in 1 microsecond with greater than 99.9% fidelity. Fidelity is essentially how accurately you can measure it. This is the world record for the fastest, highest fidelity readout of a single electron spin. And atomic engineering is what has allowed us to do that. What's really exciting for me is we've got results in the lab that actually smashed that result, but I can't tell you about them yet. But we've got a very new result that's going to come out soon. So part of the advantage here is the intrinsic potential, confinement potential. Just putting that phosphorus atom in place allowed you to capture the electron that creates the qubit. So that lack of materials interface means that we have a nice clean system without interference. But there's more to fast readout than just that. The closer you can move that qubit to the sensor, the faster you can read out the spin state. So with this atomic manufacturing we've developed, we can bring our sensors incredibly close. That's why it's so fast. But finally, we can engineer our sensors with atomic precision. And that means those sensors are highly efficient. So when an electron moves in the device, the sensor goes from completely on to completely off with very high signal to noise. So it's this atomic precision that's allowed us to get that fast, high fidelity readout. For a second result, which also confirms the advantages of having atomic engineering, we now hold the world record for the fastest 2-qubit gate. A key operation in computer logic is when we're running algorithms is to be able to swap information from one bit to another bit. This is a reversible interaction called a swap gate. And in 2019, we demonstrated by putting our phosphorus atoms just 13 nanometers apart and very close to our high fidelity readout sensors, we could swap electrons from one atom to the other in 0.8 nanoseconds. This is the fastest that's been demonstrated to date. And this was all achieved while at the same time being able to initialize and read out the individual electrons using our sensors. It was nicknamed the fastest 2-qubit gate in the West, and my students made a fun YouTube video about the result, but I did insist that they publish it, and they did actually end up getting on the front cover of Nature with that. So these results may seem technical, but they absolutely matter. There is currently a race on in the world to build a quantum processor, and different groups and different companies are all bragging about the number of qubits they've managed to bring together. The number of qubits, however, means nothing if they don't have high enough quality to work. And what will count in the long run is not whether you have 50 qubits or 5,000 qubits, but whether the qubits you have are of sufficiently high quality that they can be error corrected. Now, it might be a surprise for you to know that the world is not perfect, and that every computer, classical or quantum, relies on a process called error correction. Even TSMC and Intel, with their high-yield processors, don't guarantee that every one of their 57 billion transistors on a microchip is going to work. So to get around this, all computers rely on a process called error correction. In classical computers, this means that processes are run in parallel through any kind of computation, with multiple copies adding redundancy. The computer then looks to the answers and discards those that are different, assuming them to have incurred an error. And this process is essential for reliable computation to occur. In the quantum realm, error correction is ever more important, since errors don't just affect whether we're 1 or 0, spin up or spin down, but it also affects where that vector occurs. So it's very, very sensitive to noise. In fact, quantum systems are fundamentally much more sensitive to errors than their classical counterparts. Moreover, the impact of errors may be greater in some contexts too, given the highly parallel nature in the way you do quantum processing. All of which is to say that quality matters, and the speed and fidelity of our atomic scale systems will likely prove advantageous in the long run for this. So where are we now? If you now believe, as I do, that atomic engineering is a revolutionary capability, and that this has opened the door for an exciting new route to building an error-corrected quantum computing, I'm hoping at this point you'll want to know two things. How far have we got? What's our biggest result to date? And what's coming next? So in the remaining minutes, I will attempt to answer these questions. So first, how far have we got? In 2021, less than a decade after our team's 2012 declaration that we'd fabricated the world's first single-atom transistor, we realized our next watershed result, the realization of the world's first integrated circuit manufactured at the atomic scale. To make this device, we had to manufacture small dots of just 25 phosphorus atoms each, so that the energy levels of each dot was aligned so that we could pass the current through them. To give you a sense of how remarkable this is, these dots had to be situated with sub-nanometer precision so they were close enough for electrons to move through in a quantum coherent fashion. We also had to figure out how to tune each energy level of each dot and then all the dots collectively so that we could actually get quantum information to pass along the chain. All of this represents a significant feat of atomic engineering. But the really wonderful thing about the device, however, was it actually calculated something. We used it to run a quantum simulation algorithm that accurately calculated the quantum states of a small organic molecule, polyacetylene. This was a major result. Today's classical computers really struggle to try and simulate atoms. If you have more than all molecules, if you have more than 20 atoms in a system, it's actually very hard for a classical computer to work out how electrons will travel through them, due to the very large number of interactions between the electrons and the atoms themselves. But by placing these phosphorus atoms into silicon with precision, we were able to mimic the carbon single and carbon double bonds of the polyacetylene molecule and simulate current transfer through the molecule itself. I should add, though, in designing this device, we deliberately chose a small enough chain of the polyacetylene molecule so that we could classically simulate what the expected current would be through the device. And for those in the audience whose organic chemistry might be a bit scratchy, a polyacetylene molecule is simply an alternate single double bond carbon chain. What the quantum simulation of our device showed was exactly how the movement of electrons through the molecule depends on whether you cut the molecule between a single bond or a double bond. In this sense, our achievement wasn't just evidence of our artful engineering. It was proof that atomic circuits could actually simulate real-world complex systems. It's an approach that may, with a little more development, be used in novel pharmaceuticals, materials for batteries, or catalysts. So what next? We're the only company in the world that can manufacture devices with atomic precision. We've got nearly 100 granted patents and 50 more pending, and this covers every stage of the manufacturing process, the different architectures that we're building, the way we operate the qubits, and the little widgets along the way, the amplifiers that we're using to actually amplify our signal. Also, from our quantum analog simulators that simulate nature to AI accelerators. And we're now scaling our hardware to take on the heavy-duty computational tasks that cannot be performed by traditional computers. To manage this, we actually face an entirely new suite of problems of the kind that Trevor Pearcey would have understood intimately. The silicon processor I have been describing, manufactured with atomic precision, is the fundamental core of our quantum computer and the basis of the quantum speedup. It is the most important layer, and without a competitive advantage in this layer, the computer will not do anything. But above this and around this, there is an entire stack of associated capabilities that must also be developed. These include readout and multiplexing capabilities, which will be provided on a separate cryogenic chip used to initialize and read information onto the qubit hardware. We will need high transmission wiring with noise filtering and shielding, connecting the qubit hardware to the readout chip and to room temperature control electronics that sits outside of our dilution fridges. This routing and I/O hardware is essential to get the information in and out of the computer quickly. Beyond all of this, of course, we're also building the high-frequency, low-latency electronics at room temperature that's required for real-time accurate control of signals going down to our qubits. There are the all-important software protocols that will be used for minimizing errors, which amounts to our error correcting layer. And above all that, there are the quantum algorithms, 70 being invented today, and that will help produce our eventual applications in optimization, machine learning, quantum simulation, and integer factorization. Now, I know this all sounds a lot for a small Australian startup to be taking on, but the prize is huge. The Boston Consultancy Group has forecasted annual quantum computing revenues at 90 billion to 170 billion US dollars globally by 2040. McKinsey has independently estimated that quantum technologies could create 700 billion annually across all industries. And it's our ambition to build a full-stack quantum computer here in Australia in very much the same way that Trevor Pearcey's undertaking with CSIROC was back in the 1940s. I'm firmly of the view that Australia can compete at every stage of this global race to manufacture quantum hardware. The atomic scale manufacturing I've described today, developed through our Centre of Excellence for Quantum Computation and Communication Technology, and now spun out through silicon quantum computing, is globally unique. Yes, a lot of other alternative methods are being pursued in this field. Ion trap, superconducting, diamond, organics, and Majorana systems, to name but a few. But none of these have yet been manufactured at scale. And with world record speeds, fidelities, lifetimes, low gate densities, and device stability, we are already creating the highest quality quantum processors here on shore. We're in this incredible position because we got in early. We now hold key patents and know-how to creating barriers to entry for other people coming into the field. And this really mimics America's 20th century advantage in classical computing, where they invented the transistor and they invented the integrated circuit, and then they controlled the early industrialization of these products. As happened in the early phase of classical computing, the hardware is where the greatest value will lie and where the spillovers will be greatest. This is because success in hardware manufacturing will attract an associated industry of component manufacturers, of control system providers, of app developers, whereas the opposite will not apply. With a globally leading Australian onshore manufacturing capability, we can build a vibrant and multifaceted quantum computing industry here. While, without such a capability, the Australian quantum computing sector will end up a satellite to an industry that's largely based elsewhere. There is also a window of opportunity that works for us right now, but it won't stay open forever. In their first incarnations, quantum computers will be high-end, high-value, highly specialized products manufactured with exquisite precision in low volume and at high margins. This can be done from Australia. It is not a mass consumer product requiring high volume and cheap manufacturing and economies of scale. I'm also confident with the right product we can find customers despite our distance from global markets. As with early mainframe computers in classical computing, users will be able to access quantum computers hardware remotely, in our case by quantum as a service from the cloud, thereby eliminating the tyranny of distance which so many past Australian operations have suffered. Finally, in 2023, I shouldn't need to add that we have the people here to make it happen, because that is pretty obvious. In the quarter of a century that I've worked in Australia, I've never had a team as good as the one working with me in silicon quantum computing. They've come from all over the world, and they're extraordinarily talented and dedicated. And for the latter, I can't blame them. Together, we are working at the very frontier of what is possible. We have figured out how to manipulate individual atoms and how to store information on a single electron. I have to pinch myself every time I think about that. We're also part of a grand quest, one that involves some truly great scientific forebears, people like Richard Feynman, Wolfgang Pauli, and yes, Trevor Pearcey. And if we can succeed with our ultimate goal, the error-corrected quantum computer, well, not just Australia, but the whole world will benefit. Thank you.
Thank you. Wonderful. I mean, my mind is a bit blown. As a social scientist, I think I caught up. I'm that next level of when the adoption comes in, but I'm very, very excited about what the potential is. So you may have smelt that dinner's here. We're going to have dinner served now, and then Jordan will come back and have a chat, have a fireside chat, and we'll unpick a few more of those details. And there will be a Q&A, so please put your thinking caps on and see what you can come up with for questions.
All right. Well, thank you. That was a wonderful talk. Everybody's been buzzing about it, as you can see. And half the questions I was going to ask you've already answered, so I've been trying to think of other things. So I'm actually going to start with a technical question, because enough people have been discussing it around the room. It's worth having a go at answering it.
Okay.
And that said, I'm probably not going to phrase it properly. But listening to the whole challenge of quantum being all about the uncertainty of what state everything is in, and then being able to talk about data and reading it out and processing, how do we understand the conflict and what you've done to resolve it, if this is the right way to ask it, between the uncertainty principles, Heisenberg or otherwise, and the precision of computing, and knowing that is it a one, was it a one, is it still a one? Is that a sensible question? Or is that just delving too deeply into
No, it's not. So I think fundamentally, quantum computing is like classical computing. You input information in, you perform a series of operations, and then you read information out. So that concept is the same. The difference is that when you've got the information in, you're using these entangled states that give you that quantum power. And the question I guess a lot of people get confused on is, in the quantum world, if you ask it what it is, then it collapses it. And so then how does that work? And the beauty of it is essentially you're putting the information in, you're performing the operations, you're creating the entanglement, you're entangling and unentangling through the calculation, and at the end you ask it the question and it collapses. And so then you have to run it lots and lots of times to measure the probabilities of all the different coefficients when you ask it at the end. And so the concept is the same, but you're using something in the middle that's the quantum part that people don't like. Did that help?
So in one sense, what we're saying is we ask the same question, run the same calculation many times.
Probabilistic, yeah.
And then the weight of the outcome decides what the right answer is.
That's right. And you're trying to amplify the coefficient that's the right outcome and get rid of the other ones.
So I hope for all the people who I touched on this in the audience, I hope that was helpful to you. Okay, so the next question goes back to one of the things you alluded to in your talk. You've done this work. You've got an army of patents. You've got a fantastic team. You're leaping ahead in performance. If you go to any pundit or magazine around the world, they'll tell you quantum computing is decades away. So there are two elements to it. You can choose which way you go. One is, what do we actually do with it? And you touched on a couple of applications in your talk. But probably more interesting to me at the moment is the question of, you've got it working in the laboratory. You said it's all doable. We discussed earlier today how this could be a uniquely well suited to Australia. What does actually manufacturing the quantum componentry for your solution look like in Australia?
Gosh, that's
what sort of factories do we need? What sort of skill base do we need? What sort of investment do we need?
Yep.
Do we leverage our resource sector? Is that part of it, because it's all just silicon and phosphorus?
So look, it's a very interesting question, because I think a lot of people at the moment look at the quantum computing field through the eyes of classical computing. And they imagine that the quantum computing field is going to be like our classical computers are now. But we know that that's 70 years down the track of where it started. And so the great thing about having a silicon roadmap is that you can look at what happened in classical computing from the invention of the first transistor to the integrated circuit. And then the interesting deviation there was that the first devices they made were things like calculating machines and hearing aids. The transistors they used were not necessarily for computation. And so in the classical computing world, they got these kind of near-term applications where they could make revenue and they could start making more and more complex systems. And then they started to get computers, and the computers got more and more complex and bigger and faster. We kind of imagine now we're going to go straight to that bigger, faster computer, quantum computer that's going to solve everything. Whereas in reality, we've got the same kind of journey. And to get to the error-corrected quantum computer, it's going to take some time, 5-10 years. And during that time frame, we've got to have people that are patient. And so there's two ways to go. One is to try and look at what are the near-term applications that you can get out of quantum states that's not necessarily the computation part. And that's where things like analog simulation come in, or sensing comes in. Or you have to then focus on, you know that this error-corrected quantum computer is the big goal and you have to get there. And so then if you look at that perspective, then you say, what do you need to build the error-corrected quantum computer? And it's quite easy to map that out for this kind of full stack, all the different layers of the stack that you need. But then in order to get it working, you have to have the quality. And that's where you challenge this belief that you could just go to industry and say, build this for me and it will work. Because industry's tools that they use are far too blunt to give you the precision that you need to control the quantum world. And so we have to create our own manufacturing journey and create kind of like Swiss watch style companies where we make devices that are not mass manufactured, they're bespoke, but they work because the quality's there. So that's the kind of vision that I have.
Okay, so the first part of that, if I tip it on its head, we're looking for applications where errors don't matter much.
Or you're looking at applications where you're using some part of the quantum phenomena that gives you a speed up over classical, but it's not necessarily a full computation.
Okay. So don't forget, I'm not asking all the questions, so if anybody has a question, raise your hand. There are some roving microphones, and that's right, it's a real challenge to ask these questions. All right, so if we think about the manufacturing, there's a question over there. There's the other challenge that we're talking about today is, all right, so we could map out a manufacturing strategy, a plan that says over the next 10 years, 20 years, these are the things we have to achieve, these are the things we have to build.
Sorry, what was the question?
How big a barrier, like, first of all, do we think that Australia has the technical resources and capability, which you've already sort of said in your speech? Yes.
Absolutely.
Apart from money, which is always needed, but in theory shouldn't be a barrier. What's stopping us?
So again, I'm going to go back to that because there's multiple questions in that one question. So for me at the moment, how much does it take to build it? It's not necessarily how much does it take to build it, but can you solve the technical problems? I don't think it's going to be 10, 20 years before we get something of value. I think it's much closer than that. But what we have to do is to address what are the key problems that stop quantum computing working commercially at the moment, and it's error correction. And so if we know that error correction is the thing that we need to solve, it basically means we've got to get a quality of qubits up and our speeds up so that we can beat the errors as they come in the system. And so what tends to happen is when people get to a point, especially when they've got a company, and they're trying to sell them, even though it's not working, which is where we're at, which is a very bizarre situation that people pay money for something that doesn't work. You've got to get it working first, yeah? And so for us, we're total focus is getting the error correction, getting the quality up so that it does work, and then trying to do that as fast as possible. So I know this is a terrible thing to say, but there's kind of what I would call the glossy brochure companies that put out all these things that you can get and all these problems it can solve, but actually it doesn't work. And so you've got to get it working first and go through that as fast as possible. And I don't believe it needs this, billion-dollar foundries that people think you need at the moment, because I think those foundries are imperfect. The tools are too blunt. So you need to go and address the key issues, build it with quality of scale, with the precision that you need to get it working.
All right, so it sounds like when we get there, it's going to be a major inflection point. Like suddenly it's going to be possible, and then things can really accelerate.
I think it's just going to be just hard graft engineering to get it working.
No, I'm talking about when you get it working.
Oh, when you get it working, yeah.
That's an inflection.
Who knows what's going to happen then? It'll be very exciting.
There's a question over here.
I think I may be asking a question which you've already answered, but I just wanted to clarify an impression I got both from your speech and what you just said in answer to Jordan's question then. That if you look at the history and you go right back to even before Trevor Pearcey, we started with a dedicated machine, with Colossus, that was designed to do a very particular job. We gradually worked from that to general purpose computers.
Yep.
We have now got more computers everywhere than you can shake a stick at, in your watch, in the cameras that are being pointed at me, all over the place. Every device has some little thing. It seems to me that the way quantum computing is going to take off, it's not going to be with a bang. It's going to be with building analog type simulations. How will what your company is doing relate to what we would probably need would be the spin-off companies that see a particular problem that perhaps quantum computing could solve now, or if not now, maybe not within the next 20 years, but within the next 5 or 10. How does that kind of branching out? Because you You can't be going in all directions. You are amazing, but probably not in every direction at once.
Look, it's a great question because I think at the moment, and for those that aren't aware, there are two branches that you could take in the quantum computing field. One is this thing called quantum analog simulation, where you literally try and mimic nature and you build bespoke processes that mimic the system you're trying to solve. And then there's the fully error-corrected programmable system. And some technology, some platforms, materials can only go one way or the other. They can only be simulators or they can only be error-corrected systems. It's very rare that you can do both. And so for us at the moment, we do have the ability to do both. So it's a constant challenge for us. And I think one of the fortunate things is the things we have to solve for the analog simulator, we also have to solve for the error-corrected quantum computer. So at the moment, the roadmaps are aligned. But you're dead right. At the moment, we're going to try and find those bespoke problems, try and get those commercial, and then we'll start to get it programmable, and then more and more systems will come. But it will grow, yeah. And I'm just talking, I guess, about quantum computing. There is quantum sensing and quantum communications, which are two other fields. With the technology we've got, you could also use it for that. So, but we're totally focused on the computing aspect at the moment.
It's Peter Yates. I have the privilege of chairing Michelle's Centre for Quantum Computing. Michelle, around the table and around this room, there are both academics and investors, business people in here. And I was just sharing with a few of the colleagues in the room the journey that you went through and your decision to bring business people onto your advisory board, Doug Elix, Stephen Menzies. I also had the privilege as well. And then the transition that you went through from having ARC funding to establishing a $100 million commercialisation vehicle on the side. It's a journey that I've tried to describe here a little bit, but I don't think many in the audience fully understand how you managed that. Yeah. Would you share that with us a little bit?
Yeah, sure. So thanks for the question, Peter. I guess so for me, I've been in a Centre of Excellence since 2000, and the Centre of Excellence is a fantastic Australian scheme. It gives you lots of researchers working on big, ambitious projects together. It is the flagship of Australian research for me, and so it's really allowed us to tackle things that honestly in other countries they cannot do in the same way. And so getting into quantum computing on the ground level is because we had the Australian Research Council supporting those schemes. I guess for me, having now been director since 2009 pretty much, I realized that we were building these new technologies, making devices that were globally unique and with this massive transformational capability. And I honestly felt this tremendous responsibility of taking all that money and then it just ending. And I felt that was just the worst thing that could happen. I guess I'm not born in Australia. Being not born in Australia, but now an Australian citizen, I feel immensely proud of Australia. I feel it more deeply in my gut than most Australians that I owe it to Australia to give back what I can do in this space. So that sense of responsibility and that sense of being Australian meant for me that I had to make sure that I didn't drop the ball on this for the research team that we have at the Centre of Excellence, but then also for the nation. They've invested this money in something that could be truly transformational. So back in, I guess, 2014-15, I recognised that, the Centre of Excellence will keep going. At some point, they're only 7-year programs and they will stop. And then what happens? And there's a gap between the end of the Centre of Excellence and venture capital. And typically what happens in Australia is most people will take venture capital because there's no alternative and they end up giving most of the company away. And so for me, I felt that was just absolutely tragic, especially because we'd had such long sustained funding. So I said to the government, this is where we're at. If we do not do something with this technology, it will go overseas. There's lots of people now chasing us, picking up the technology globally. And so the kind of message I got from the government was, get some commercial backing, have someone that supports you commercially. And we had already in 2012 had the Commonwealth Bank come and visit us and had seen the research we'd done and said, we've heard that quantum computing is the next great thing. We've got into cloud computing at the right time, and we're overseas looking at all these American companies, and they tell us, actually, you guys are leading in Australia. So we're coming back now and seeing if we can invest in you. So they literally walked into my office at UNSW, which is quite an unusual thing for the CEO of the bank to come in. And I then went to the bank and I saw just how amazing that organisation was. Then Telstra came in after that, and basically the government said, if you can get the companies to get behind you and the university, then we'll match it. And so that was the deal that we did back in 2015-16 with the NISA, I can't even remember what it is now, Innovation Science Agenda. It's a National Innovation Science Agenda. And I guess part of that journey was throughout the whole process, that one thing, as you will know on the board, is I felt that, being an academic, I didn't know who the right people to have on our Centre of Excellence board. So I literally went with the people that I felt had the biggest experience, that were enthusiastic about what we did. And obviously you came on the board. We've had people from, top corporate lawyers come on the board, people that have been on IBM boards. And they basically got behind me and said, don't stuff around. This is too valuable. We'll support you. We'll go down with you. We'll talk to government. And then basically over a period of 4 or 5 years, we got that co-investment for the 83 million back in 2017. And that really kick-started the company. And again, that for me, just personally, that responsibility gene is still there. Every day I want to get to work because I have that responsibility that I owe people to produce the computer that I think we can make.
Great. And the next question is over here, Jennifer.
Hi. You said that you would need to make a very small volume of bespoke parts. Could we 3D print them now that we can 3D print at a nanoscale? And no, not possible?
Not yet. So the tools that we use at these microscopes, this fine metal tip, that's what gives us the precision. And so that tool, it's quite unique in that you can, just let me give you this a bit of a history. So I would go to semiconductor manufacturing plants and I would go and look at how they do things. And so I was very lucky. IBM went through their 500-step process. This is how we manufacture. And so I got an insight into all the different tools they have and how they work. But I saw then the resistance to taking on new tools to fit into their foundries. And so our tool that has that precision is very hard to put into their process because they've got cheap mass manufacturing and we're going bespoke single atom precision. It's the exact opposite mindset to what they had. And so when I went there, 15 years ago, they thought I was kind of cute. I had this little technology out in Australia. Look what they're doing, but now when I go there, they have STMs in their manufacturing plants and they use them in a different way. They don't use them in the way that we use them. They use them as like a medical tool. So when their chips don't work, they literally dissect their chips and they use these tools to figure out what happened as to why it doesn't work. So slowly but surely this technology is coming in, but not in the manufacturing approach. So it's a change in mindset to go from these big mass manufacturing to these precision bespoke tools.
Our next question is over here.
You've done very well and figured out the funding model to date. And as we look at industries like quantum, this is attracting international attention, more international money. Do you think there's a risk that there's not enough private capital in Australia willing to back these industries so we have the local support for it rather than it all being international money at this point in time going forward? And is that going to be a risk to the country?
Yeah, it's a great question. I don't honestly have an answer at the moment to that question. I think, so for us at the moment, we've just finished a capital raise. We're sitting in a position where we just have to move fast. I firmly believe that technology will speak for itself, so it's got to be all focused on the technology. In the meantime, the world will move by the time we're out capital raising again, and we'll see where we land at that point. But I think at the moment, it's complex. We don't necessarily want to take venture capital from overseas because you end up giving it away. But at some point, you have to back the technology. So it's going to be a complex journey. And I think every quantum computing company is on the same complex journey. It's not easy for any of us, I don't think.
And if I can say, we were talking about this earlier today, and my response was, you've all been reading in the news about Twiggy Forrest and his heartfelt press for hydrogen. Whether you agree with it or not, we need to find the Twiggy in Australia. I don't know if that means it's Gina or one of the other billionaires, but we have to find someone who sees this opportunity and can have that same passion and dedication. To me, that's where you find the success in funding from within Australia. It's not going to be from government, and it's probably not going to be from most corporates because most of our corporates aren't in the industry side. So the people funding it now are fantastic. I don't know if they're going to be the ones to step up with that next level of funding, but I do think we can do it for sure. Another question over there.
Hi.
Sorry.
Do you foresee a point when you'll be able to use the technology to accelerate the technology itself?
Oh, yes. Yeah, absolutely. I think when people used to ask me, what are you going to use the technology for? My joke, which was real, is to help build itself. And so every device we make, we understand how to make it better. And so literally, we've recognised that one of our competitive edges is just to go fast in the manufacture. We control all aspects of manufacturing. We can prototype very quickly. And so we learn every device we make how to make the next best device. I think one of the things that's probably not well known is that because the devices are so small, they can be simulated by classical computing. And so we can actually use classical computing to model our systems and then create a predictive model about how it should behave. Most systems that people are using are too big to do that, so they can't get a good handle on what happens as they manufacture. And actually, to be honest, most companies outsource their manufacturing. And so that's the other competitive advantage we have, is that we don't do that. We control every aspect. And I think that's quite critical.
Another question over here.
Hi, Michelle. Hey. I'd like to preface this by saying this is a controversial question, but it's asked on behalf of this table.
My table.
Because I would like
okay,
to
guys.
be friends with you. So we talked about how Australia's become your adoptive home. I just want to see how Australian you actually are. Recently, the Matildas played the Lionesses. Who did you actually back?
I said this was a moment for me, and the guys, some of them know this story at the table, because I got a call from the British High Commission to go and watch the game. And I said, okay. I said, yes, because I wanted to see the game. Who would not want to see that game, yeah? And then I said, can I wear whatever I like? And they're like, oh, are you going to come in the England colours? And I said, well, no, I'm going to be in the Matildas colours. And they, anyway, they were a little bit hesitant. They said, well, no, you can't come then. And then for a moment, literally, I thought, are they joking? Are they serious? And then I thought, I'm just going to have to go for it. So I turned up full in the Matildas outfit, and it was great. It was a fantastic game. But I have to tell you, so anyone that saw Sam Kerr score, fantastic. I mean, like, we were all up out of our seats. But it was amazing, because when England scored, it was the weirdest thing. It was total death hush. And these guys looked at me and they said, did we score? Did we score? Like, yeah. No, but I've truly flipped.
Okay. Thank you. Another question.
Yes, hi. So I'm Nick Menacucci. I'm a professor at RMIT, and I know Michelle quite well. So Michelle, I just wanted to give you an opportunity to talk a little bit more about the broader ecosystem of quantum technology, because what I've heard you say was related to your own company, which is a fantastic case study, and its commercialization. But I'm wondering if you could go sideways from that, like talk about how the funding for quantum computing over the years and over the decades has engendered new technologies, not just the ones that will occur 10, 20 years down the road, but the ones that are occurring now or in the medium term, and why it's important to fund all of that, assuming you agree with that.
Yeah. So look, I think when I first arrived in Australia, just in general actually, I was lucky to tour the country, and I saw amazing research everywhere. And I realized that story is not well told. And so certainly in our Centre of Excellence, when I arrived here, there was a group that was trying to build silicon quantum computers. But to be honest, everyone that was in that at the beginning, none of them had silicon experience. So that was quite interesting. But perhaps the stronger team at the time when we arrived in Australia was Gerard Milburn, who was an optical quantum computing specialist. And so he had built, I guess, based on the quantum optics experience in Australia at that time, he had built a big group at the University of Queensland, which has now grown across the country. So there's groups at ANU, RMIT, so now all trying to build optical systems as well. And for me, that's been kind of a fascinating journey. You can encode information in photons of light rather than spins in a semiconductor. So it's a completely different way of doing it. That group has grown phenomenally. There's been 2 startup companies that have come out of that. So one of them is PsiQuantum, which has now moved to the US, and one is Xanadu, using different ways of encoding information. So, you know, Australia, when it looks back at its history, optical quantum computing is something that people would definitely say is a major strength. But then also, in our Centre of Excellence in 2011, we brought in secure communication systems. And so there's a group at the Australian National University that send information in photonic states, so that if you try and attack that and get the information out, it collapses. So you can send information absolutely securely. And so there's a big team at ANU. But even more than that, so since I've been here, there are now, you know, our Centre of Excellence is in its 3rd round, but there are now 6 centres of excellence that have quantum physics at its core. So there are literally thousands of quantum engineers and scientists across the country. There are, I don't know how to describe it, there's been probably more than $500 million spent in quantum computing and quantum information in Australia. And so when I go globally, everybody knows that this is a powerhouse. It is a talent pool. We are perceived as a talent pool. So we do have to be careful because people come over here and try and take our fantastic researchers away. And so I've learned the only way to stop that is to be at the very forefront because that brings them in. So you just got to keep moving fast. But yeah, Australia is in a phenomenal position for quantum.
Wonderful, and I hope very inspiring for everybody. Question over here.
Thank you, Michelle. That was an amazing talk. My name is Kwang. I'm with Melbourne Business School. And I'm going to say I'm sharing this question with Carl from RMIT because it grew out of the dinner conversation. And it's about what else needs to change in the Australian ecosystem for this to succeed. And the source of this question is that all new technologies need a change in the surrounding things for it to work. For example, how do you debug something that is written for quantum? It's superposition, all happens at the same time. Is the software something that requires new skills, and are we set up? So I guess the worry is that we'll have the hardware and then someone else will run away if we don't have the rest of the stuff to get it all to work. And you being the expert, could you tell us what else do we need to get in play surrounding this for it to succeed in Australia?
Oh, so that's a complex question. And the reason why it's complex is at the moment there's, I guess, a big debate in the quantum computing field about whether you need to have a full stack company with everything integrated in one place or whether you can have this kind of Lego block approach to stacking all the different components and have different companies in different layers. It's completely divided, I'll be honest with you, so it's a kind of a contentious discussion. But in general, just from pure experience, I know that having everything in-house basically means that every time we make one layer work and we make the next layer up, it makes the lower layer better. So bringing it all in-house for us has meant that we've gone faster and that we don't have to wait on other people. That said, at the higher layers of the stack, in the software layers and the algorithms, it's much easier to work across different platforms. So that's an area where Australia has great strengths in error correction, in software, and in algorithm development. And that's something that you could, in my mind, if I had the ability to do whatever I wanted, I would create just one national team, everyone in it together, working for all the companies that are here. That's what I would do.
Excellent. Well, we've run out of time. No, we've got one more. Okay. Carl gets a question anyway.
Some of us in the room have spent 40 or 50 years trying to change government policy on innovation and R&D and stuff like that.
Yes.
What I worry about is that there are countries in the world that don't believe that it's necessary to wait for the private sector to want to come in on a project like yours. And what's the risk that you face in terms of a government somewhere else in the world that doesn't have the same free market view that we do, looking at this kind of activity or any other and saying it's so important, we'll put up the money to get it started and to a commercial stage, and then we'll sell it.
So you mean taking Australian technology overseas? Is that what you mean? So I'm not sure I understood that. So taking Australian technology and commercialising it overseas, is that what you mean, or?
I mean, the Singaporean government took the view at some stage that it would develop industries and then flog them.
But are you asking, is the concern about another country replicating this work and flogging it, or acquiring this work?
No, well, that's acquiring the work is going to be a risk anyway. But what the other risk is that other countries that are more proactive in technology development might decide to fund the activity themselves, develop it themselves, without waiting for their private sector, which is reluctant to invest in this stuff, to do it.
So replication.
Yeah, so look, I think, honestly, since we started this program 20 years ago, there's been multiple people that have tried to replicate. And so and at the beginning, it meant that I think in a defensive mechanism, Australia typically then tries to not collaborate and go internal, which I don't think is necessarily the right way to go. But honestly, the most important thing is that you have speed. You just have to move fast. And so I honestly believe if you have technology that's at the forefront and you're committed and moving fast, then you will be able to create the capital when you need it. You know, it's not easy, and so I can't hand on heart say I know where the capital is coming from next time I do this. But if you totally believe in it and you're at the forefront and you've got the best technology, then I think you will push it. And so I don't think you can hope that things are going to work out, and I don't think you can spend time lobbying government forever. I think you just have to go with the free market when it gets, you know, when the rubber hits the road.
Is it perhaps just very quickly reflecting on your Sandia story in regard to competition?
Yeah, and just to give you a sense, so there's multiple groups have tried to chase us. So a big team in the US tried in the 2000s to replicate, and they couldn't. And at that time, we were, you know, keeping patents and secrets. But since that time, we realized that no matter how much you try and patent and keep things secret, people will be able to replicate. So you just got to move. And so that's, you know, that no one yet has caught up with us, but there's been multiple teams trying. So speed is everything.
Well, I'm sorry, but we're out of time. So would you all join with me, please, in thanking Michelle? And just as a small token of our very great appreciation, I hope you'll enjoy it.
Fascinating. Thank you very much, Jordan and Michelle. That's quite an experience tonight for all of us, and we're very privileged for you to share with us some of the challenges and successes you've had to date, and we wish you well for yourselves and your team over here. I've been talking to some of your team over here. Fantastic, and hopefully for Australia we can capitalise in this. There's a number of other people I'd like to thank this evening, in particular Didier. Thanks very much and congratulations on we have National Entrepreneur of the Year awards, and we'll be making those on October the 30th. We have Entrepreneur of the Year in each state. So 7 a year. We've been doing this a number of years. So we've got a lot of wonderful people that have come across in presenting the true capabilities of this nation in entrepreneurial, high-tech entrepreneurial activities. So the Minister had to go, so we really appreciate that he actually turned up, and also the Vice-Chancellor, Duncan, he's got an early start, so he had to bid farewell, but I told him that I think he and I agreed that both England and Australia will not be in the finals of the rugby. I'd also like to thank Amanda Capels from the lead scientist for the Victorian Government, who also came along with us today when we were down at Science Works. I'd like to thank Kelly, Jordan and Karen. Where are you, Karen? Oh yeah, Karen resides in Caloundra, but she managed to escape down back to Melbourne for a bit, who put this evening together. To Melbourne Connect, thank you very much for a great hosting and a great facility. And to the Churchill Club, who's also helped us promote this event, and especially to the ACS Victoria and National, who've all rallied around to help us make tonight a great success. And to all of the friends of Pearcey here this evening and who viewed tonight's proceedings online, if you're still there, thank you very much. This is a all volunteer group, and we've been at it for 25 years, but I can tell you it doesn't get any easier to make all these happen. It's all volunteers. We work, great team effort right around Australia. And in particular to those Victorian government folks who've worked so hard these last 14 days to make the 2023 DIF such a success, and I'd ask you to thank them with applause. Now, I mentioned earlier on we're having an Australia 4 summit on October the 30th, which will be the same day as our national awards in Sydney, and I'd encourage you to look on our website, book in and celebrate with us for the summit and for the awards dinner in Sydney. Now, just before I invite Jordan back, I've just asked my colleague Peter Thorne to step up here for a moment.
like this.
Yes, right. So Peter's got a few words.
My only words are thanks to Michelle, and I have a precious artefact, which is a very rare copy of the book on CIRAC, signed by the original engineers, and not all with us anymore, I have to say, which we think you're an appropriate recipient.
And so, just to wrap a bit, I've asked Jordan back up to a little surprise here.
So as you heard at the beginning, our MC, Kelly Hutchinson, who told you that she spent 10 years as the Deputy Chair of the Pearcey Foundation, and this year her career is continuing to grow and change, and she's stepped down from that particular responsibility. And so I'd like to encourage all of the members of the Pearcey family who are here, so Peter and Rick, if you would stand up and join with us, and we'd like to invite Kelly to the stage for a thank you.
What a memento.
Everybody who knows Kelly knows that red is her colour.
There's some things in it.
I'm sure there are. Thank you. Thank you so much for saying something.
If you want.
Well, you know, I'm always going to say something. Thank you so much. I was adopted by Pearcey Foundation the day after the last iAwards I worked on. And it's been an absolute honour, and I do thank my mentors and my chairs and my board who have buoyed me through this experience. But it's been an honour, and I'm still a friend of Pearcey, and I will be around again still. Who knows? You may see me in Sydney.
Just behind the corner there. And then one last item, none of this would be possible if it wasn't for the support of Karen Nelson, who's been working in the background tirelessly with us to pull everything together, to make this happen, to make our other activities happen, to organise everything that's been going on tonight for us. And so a token of our appreciation, Karen. And that's it. That's a wrap. Thank you very much for coming. There's plenty of opportunity to stay and chat and speak to each other. I encourage you to discuss anything and everything that's on your minds. Thank you very much for coming. Good night.